So next, Chem 100. This is the last chapter that will be covered on exam 1, chapter 3. And we're going to discuss matter. There we go. It's a fairly short topic to cover for this class. So that gives us plenty of time to chew on each item. So, as I mentioned in the at the close of chapter 2 lecture, matter is anything occupying space and also has mass. That's the simplest definition and the one that I've heard since I was that high. We're going to be interested in matter in terms of its states, and we're only going to be considering 3 normal states that occur under normal laboratory conditions. And that is solids, liquids, and gases. There are other states of matter in the universe. In fact, there are other states of matter on Earth, but they're artificially produced. For instance, if you've ever had your exhaust system worked on at a muffler shop, and the technicians can't get your muffler loose or can't remove the tailpipe to replace it because maybe the bolts are rusted solid, they'll take this device called a plasma cutter. And basically what it is a tube attached to a nozzle, and the nozzle squirts out argon gas. And also at that nozzle is a high voltage direct current discharge. So it sends massive amounts of electricity through that argon gas and produces an ionized argon jet. And that jet will cut through your tailpipe or your muffler like a hot knife through butter. That's a plasma. We're not interested in plasma for this course. So what do these 3 states of matter look like on the microscopic level? The solids are regularly ordered molecules or atoms. In this case, we're looking at water, and I'll say another word about water in just a second. The liquid water is still composed of water molecules, but they are able to move past one another easily. They're very close together, but they're not locked in place. And this is characteristic of any liquid. And that means that the liquid has approximately the same volume as the solid, but it cannot hold its shape. It needs a container. There's a big jump from liquids to gases in the spacing of the molecules and in their velocity. There's lots of difference between distance between gas molecules, and they're moving very fast. In my other chemistry class, we actually calculate the average speed of a gas atom. And we use 2 or 3 examples because depending on the size of the atom, it will move at different speeds. But one of the speeds is pretty close to the speed of sound. So there's the difference. Solids have a regular shape, and they maintain their shape, and they have a fixed volume. The liquids have a fixed volume, but they don't have a fixed shape. They need a vessel. And gases don't have a fixed shape, and they don't have a fixed volume. So they need a completely enclosed vessel to contain the gas of interest. Okay, this is the black and white that tells you what I just told you about solids. Some examples: ice, diamond is a solid. An iron bar is a solid. I'd rather have a gold brick. That's a solid. Liquid. There it has the definite volume, but no shape. It always assumes the shape of the container. And gasoline's a liquid. Water's a liquid. Alcohol's a liquid. Blood is a liquid. Another interesting characteristic of liquids is no matter what the shape of the vessel, they always maintain the same height in the vessel. So if you have a liquid, in this example, the liquid is distributed among 3 different shapes, and they're all at the same level. Gases have no fixed volume and no fixed shape, so they will assume the shape of the vessel and the volume of the vessel in which you place them. If you put a small amount of gas into an evacuated cylinder that's this big, it'll expand to fill it. So what that says about the molecules of a gas is that there's lots of space in there compared to the size of the molecule. Plus, they don't interact strongly with one another. Liquids and solids interact reasonably strongly because they stay close together. But gases are so far apart, they're moving so fast that they don't interact much. Take that with a grain of salt. They do interact some, but not much. And that's why they will expand to fill the space. In fact, when gases were originally investigated back in the middle 17th century on a scientific level, gases were all treated the same, and that was fine under the conditions of room temperature and near 1 atmosphere pressure. All gases behave the same. They behave as if there are no gas particles there, right? It's just the space is the gas. Now we know the particles are there, but you can treat them experimentally as if the molecules don't exist. That's also known as an ideal gas. So the air we breathe is a gas. Helium filling party balloons is a gas. Oxygen from a cylinder that keeps people from suffocating. If they have asthma, if they have COPD, if they have some other lung condition, then extra oxygen helps them survive. Now let's talk about properties of matter. First, we'll talk about physical properties. Okay, physical properties of matter are those characteristics of matter that can be changed without changing its composition, without changing its identity. When we identify matter, we say, this matter is water, for instance. Okay. If we do anything to that water that changes its state or changes anything about it, except its identity, it's still water no matter what we do to it, that's a physical property. It's identified as a characteristic. Now, the change doesn't have to occur. The physical property speaks to potential change. And these characteristics are more often than not directly observable. We could say the substance has a certain color. Its physical property, it has a mass, it has a volume, even a temperature. we could identify those as physical properties. Now, those properties can change. The color could change. And if it does change, then if the identity of the substance remains the same, then that change is physical. You ever see butterflies? Notice butterflies in the sunlight, depending on which way their wings are canted, will change colors. It's a physical phenomenon. The scales on their wings act like diffraction gratings, right? I don't know if you've heard of diffraction gratings, but it's another way of splitting white light out into different colors, like a prism. But there was no change in the identity of the butterfly wing. Its composition is the same. So that's a physical property. It has the ability to alter its color with the angle. Some other examples. We mentioned color, we mentioned volume, states of matter. Density is a physical property. Mass per unit volume, so many grams per cubic centimeter, is an expression of density. Melting point, boiling point, those are physical properties. They don't change. Some of them don't change no matter what we do to them. Melting point, melting point won't change with air pressure. Boiling point will change with air pressure, but the substance identity does not change. For instance, water boils at 1 atmosphere, say sea level. Water will boil at 100 degrees Celsius. If you increase your altitude, say go to Denver, Colorado, it's about 1 mile high, the boiling point will decrease significantly. I don't remember offhand what it is, but I do know that if you try to boil an egg in Denver, it takes longer than it does to boil an egg in Savannah, Georgia, right on the ocean, because the boiling point has changed. But the water, still water. The identity of the substance hasn't changed. Chemical properties. Chemical properties are speak to the potential for the substance to undergo a change of identity and the ability for it to form new substances. Now, again, we're talking about a property, so we're not saying that the change occurs, it's just the potential to occur. It may, and very often does, speak to the reactivity of a substance. For instance, sodium metal can react with water very violently. That's a chemical property of sodium. We didn't say it changed. No, we haven't done the change, right? We just say it has the potential to change. Other characteristics that describe a change in identity might be flammability. Right? Gasoline in your tank of your car, is flammable. Right? Hopefully, you don't experience that except inside the engine. Steel will rust. That's a chemical property. The food that we eat is digested. It has the potential to be digested and provide us with energy, building materials, and other nutrient items that are needed for our metabolism. That's a potential, that's a chemical change. Chemical property. Our food, the food that sits on that table, has the potential to nourish us. That's chemical property. So let's see if we can identify each one of these as either a physical or a chemical property. Ethyl alcohol boils at 78 degrees Celsius. That's a physical property because even if ethyl alcohol boils, it's still ethyl alcohol. Diamond is hard. In fact, on the Mohs scale, diamond is the hardest. Oh, got a visitor. Here we go. Let's see, let me pin my video. Okay, well, I'll mark you as present. Zooming. So I've been at it for about 17 minutes, but it's all recorded and will be posted in Brightspace. There's no requirement that you attend in person or by Zoom. Of course, you can attend any way you want to, but if you want the interaction, then you're welcome. Welcome to come this way. Let's see. I think you've just been added to my course, correct?
Yes, sir.
Okay. So did you have any trouble in Brightspace finding the materials that you need?
No, sir.
Okay, good. That's fine. If you come face to face, I have copies of things that I hand out, but everything that I hand out is also in Brightspace, so everybody has access to it.
Okay, thank you.
All right, so we're up to the point now we're trying to distinguish between physical and chemical properties, and I've defined them in a couple of previous slides. And we identified ethyl alcohol boiling at 78 degrees Celsius as a physical property. Ethyl alcohol has the potential to boil, and the identity of the ethyl alcohol does not change in the process. Now, we're not saying the physical property that we've identified says that it has the potential to change, but it hasn't changed. We just say that it could change if we proceed. That's the difference between a property and a change, and we'll cover changes in just a minute. The hardness of diamond, in fact, on the Mohs scale, diamond is the hardest member of that scale, number 10. And number 1 is talc. It's the softest, and they're a grade of different things in between, but each substance has its own value for hardness, and that is a physical property. Sugar that ferments to form ethyl alcohol. Sugar it has the potential to ferment, and when it does, it changes its identity. So we've identified a chemical property of sugar. It can change into something else, into a different substance. Okay. Now, when we talk about changes, we're actually identifying the actual process of change. A physical change maintains the identity of the substance, but it undergoes an observable change of perhaps state or some other observation like color or let's see, we've got some examples here. There's your change of state. Okay? That is a physical change. Something has occurred and we described it. Is that all there is? I thought I had more examples than that. So here we have 3 states of water, physical states, and to change from one to the other, more often than not, the temperature changes. That's the single most important deciding factor in a phase change is temperature. What's interesting about water is that as it goes from a gas to a liquid, of course, we call that condensation. The molecules get closer together, but they still can't maintain their own shape. They need a vessel. And as we cool it down at less than 100 degrees Celsius, water will convert to a liquid. If we go from a liquid to a solid, say from liquid water to ice, the water molecules assume a regular structure. Now, what's interesting about water is that it doesn't just get close and stack the water molecules like this. It assumes a regular structure in the form of a hexagon. And that's what this inset is trying to show. Water arranges itself in a hexagon, 6 sides. So that's why snowflakes have 6 points on them. They have 6 sides. It's based upon that microscopic structure. But what also happens is you get this extra space built in to the structure. So what happens because of that is the density changes. Density is mass per unit volume. So the mass of the water doesn't change, right? If we have a sample of liquid, a certain amount, and it freezes, the mass didn't change. The volume changed. And the volume increases as we go to ice. So what that means is that the density of solid water or ice is less than the density of liquid water. And the practical outcome of that is that ice floats. And it floats because of this change in its structure, adding volume. And of course, it's fortunate that ice does float. If it was like most solids, the solid would be a little bit denser than the liquid, and it would sink. So it freeze and sink, freeze and sink, freeze and sink. Pretty soon, all the lakes and oceans on the earth would be frozen solid, and we'd be in big trouble. Okay. So in a chemical change, the identity of the substance does change, and we describe the chemical change in terms of what the new substance is. So an example would be in a Bunsen burner. You've never heard of a Bunsen burner. It's one of the items we use, pieces of equipment we use in the lab to generate heat. And it just takes natural gas and controls the input of air and gas so that you can get a usable flame. Well, the flame is composed initially of methane and air. And the important part of the air is the oxygen. So it's methane and oxygen, and they combine, they react, and they produce water vapor and carbon dioxide. So there has been a change for the methane, for instance. The methane has changed in the presence of oxygen to these other substances. Its identity changed. That's a chemical change. Here's another way for a chemical change to occur. Let's go one way first. I'm going to write out the reaction, and you haven't learned how to do this yet, but that's okay, it'll come. If we take hydrogen gas and add it to oxygen gas, we will get water gas because it's really hot. Now, if I balance this equation, I'm going to do a 2 there and a 2 here. Okay, so we're describing a chemical change going this way. And in fact, that's what happens. It still happens. Some rocket motors are powered by liquid oxygen and liquid hydrogen. And by the time it gets to the combustion chamber, it's turned into a gas. But the space shuttle had 3 main components. It had the shuttle itself, thing that looked like an airplane. Then it had this big orange tank. That's where the oxygen and hydrogen were stored. And then it had two solid rocket boosters on the side. So when the rocket motors, the main engines, drew hydrogen and oxygen out of that big orange tank, it underwent this reaction. And it's very energetic. It produced a lot of thrust, and that's that in combination with the solid rockets sent the shuttle into space. Unless, of course, you have a breach in the solid rocket, it burns through an O-ring and then burns through your orange tank, and it mixes the oxygen and hydrogen catastrophically, and then you have a Challenger disaster. But under control, it's supposed to produce water and a lot of energy. Well, you can go in reverse too. You can take this water. This is going to produce a lot of energy. But you can go back this way. If you put energy in, you can split the water molecule into hydrogen and oxygen. And that's what this device does. It sends a direct current between the two electrodes. And at one electrode, you get hydrogen, and the other electrode, you get oxygen. That's called electrolysis, by the way. But water has undergone a chemical change in electrolysis. Hydrogen and oxygen undergo the reverse chemical change when they're mixed and ignited. Okay, so this is an artist's representation of this reaction in reverse. So here we have the two water molecules, and we put energy into them, and it splits them into one oxygen and two hydrogens, where you have a hydrogen molecule will have two hydrogen atoms together, and the oxygen molecule will have two oxygen atoms together. And when you start to learn the chemical symbols, and there is a document, let me see. Let me illustrate my point with and I'll get to it eventually. Here we go. So this periodic table right here is available under the module for exam 2. But if you want to get started memorizing those symbols, that's okay. You can go in and get that periodic table, and the ones that are marked in red boxes, only the ones marked in red boxes, are the ones I want you to learn. You can make flashcards, and it should come fairly quickly. But the sooner you get started, depending on how quickly you pick up new things, if you can start later if you want to. For me, I would have to start now and work on it for a couple of weeks to get it all done if I didn't already know them. But those are the ones, there are about 60 of them. Those are the ones I want you to memorize. And you'll also notice that some of these have blue highlights over here and hydrogen. Those that have blue highlights, under room temperature and 1 atmosphere conditions, they're always diatomic. That's why I write oxygen O2 and hydrogen H2. They are diatomic. When we say in a word problem, if it said hydrogen and oxygen are mixed together to produce and reacted to produce water, then you would have to know that hydrogen is diatomic, oxygen is diatomic, in order to write the correct chemical equation. Okay, so that it's important to memorize those and take special note of those diatomic elements. Okay, back to the slides. So let's see if we can identify how many of these are examples of chemical change. Okay, if we pulverize or crush rock salt, the question you ask yourself is, did the identity of the substance change? No, not in this case. It just got smaller particle sizes of the same substance, rock salt. So that's a physical change. Let's see, do I have those identified? No. Burning of wood. If we ignite wood in a fireplace and burn it, then it undergoes a change in identity. The wood now is reacting with oxygen, producing heat, producing carbon dioxide and water, and some ash. So that burning of wood is a chemical change. If we dissolve sugar in water, what has changed? Only the state, right? Water is still a liquid, but sugar was a solid and now it's part of the liquid. But it's still there. Now the question arises, how do you know it's there, right? It's in solution, you can't see it. So how do you know the sugar didn't change on the way in? All you have to do is evaporate the water. And you can catch it, condense it if you want, but what's left behind is sugar. And you can test it and find that the sugar you put in is the same sugar that comes out afterwards. We can separate these mixtures. If it is a mixture, we can separate it by physical means. Just evaporate the water. Melting popsicle on a warm summer day. That just changes the state. The components of the popsicle are still the same. You still got water, still got sugar, still got coloring, maybe flavoring of some kind. But the identities did not change. The only chemical change in that group is burning wood. Okay, we get another chance. Physical or chemical change. Okay. Sugar fermenting to form ethyl alcohol. That's a chemical change. We have changed the identity of sugar to ethanol. Right? Iron metal melting. We still have iron. The identity of the iron is still there. Now it's just changed its state from solid to liquid. So that's physical. Iron combining with oxygen to form rust. That's chemical. Iron is no longer iron, and oxygen is no longer oxygen. They have formed another compound, another substance called rust. I used to live in Atlanta. In fact, I grew up in Atlanta, Georgia. And there was some bright architect who had stumbled upon a substance, a material that he could use in constructing a building. And it was made from steel. And you could clad your building with steel, this special steel, and it would rust really fast. It would rust so fast that the idea was that it would rust fast and seal the underlying metal against oxygen getting in and continuing to rust. Okay, so it was a good concept. The firm convinced somebody that they could build this building, so they built it. And they called it the Omni. It was downtown Atlanta, and in the Omni, they had basketball games, the Atlanta Hawks. They had, for a time, they had the hockey games, the Atlanta Flames, and some other activities, concerts and so forth. What they didn't count on, though, was that Atlanta gets 60 or 70 inches of rain every year, and it usually comes in huge downpour. So the building did what it was supposed to. It rusted, converted the iron into iron oxide or rust, and it looked great in the beginning. It was like brick red, beautiful, until they got their first rain. And it washed the rust off onto the concrete and streaked this ugly red stuff all over the concrete. So to make a long story short, that building was torn down. They replaced it with something else. All right. There we go. All right. So what is matter composed of? Right. We've just been talking about matter in general and inferring some chemistry along the way. But now we need to get to more specifics. And an element is any substance that cannot be broken down into other simpler substances by chemical means. So if we have hydrogen gas, we can't do any chemistry with it that will break it into something simpler. And say we don't know that hydrogen or oxygen are like that. Say that's just, we have characterized and named them. And we try to by all chemical means to reduce them, say split them into two different substances or whatever the case may be. We can't do it. So they are identified as elements. Through the Middle Ages, alchemists were mixing things up in their kitchens, and they had identified several elements even before modern chemistry came online. So the elements have been with us for a while. Some elements occur naturally in pure state. Gold is that way. So that's why you can go to, say, California or Alaska and pan for gold and get pure gold flakes or nuggets. Most elements, though, however, are combinations. So when you have a substance and you try chemical means to break it down, most substances naturally occurring on the earth, you can break them into simpler substances. Right. So here's some examples: iron, aluminum, oxygen, and hydrogen we just talked about. Those are elements. Right? They cannot be broken down any further. The entire universe is composed of elements, various mixtures of elements. Stars are primarily hydrogen with some helium. 90% hydrogen, and the rest about 10% helium. There's some other elements in there, but they're only minor components. Gas giant planets like Jupiter, they have large amounts of hydrogen, some helium. They also have some water. We've sent space probes into the atmosphere and picked up these elements in their atmosphere. You can also detect them with telescopes. You can see their light signatures, and that's another subject. But they've got, Jupiter has mostly hydrogen and helium, and they have water vapor, ammonia, some compounds of sulfur. Some of them are elements and some of them are not elements. A compound, though, is a substance that's composed of a combination of elements, two or more elements together, could be 2, 3, 4 elements or more, combined in such a way that they bond together. And we haven't talked about bonding yet, but just set that aside for the moment. They are bonded together to form a new substance that has characteristics unique. It's different from the elements from which it's composed. And it can be broken down. It can be split, broken down into those elements. So that's what we did with electrolysis. We took this compound and broke it down into these elements. Now, these are not compounds because they're bonded together, but they're the same element bonded to itself. And so these are elements. This is a diatomic element. That's a diatomic element. Compounds have to have two or more different elements. Water is a good example. Carbon dioxide, table sugar, sucrose is a pretty big compound. You see it's got 12 carbons and 22 hydrogens and 11 oxygens. All right. Another interesting characteristic of compounds is that they always have the same composition of the elements of which they're made. In fact, the law of constant composition or definite proportion, is two ways of saying the same thing, was established in the 1700s by, I think it was Lavoisier. And all it says is that these compounds, no matter what their source, in fact, you could purify water from the lake, and that would be water of a certain composition, a mass ratio of hydrogen to oxygen. You could make water by burning hydrogen and oxygen, and that water will have exactly the same mass composition as the other water. Okay. So once the compound is identified, that ratio of mass of element to element is fixed. It's the same. Now we know with the developments of modern science over the years that the reason that these compounds have constant composition is because they have constant numbers of atoms of those elements. Okay. Okay, how many of the following are compounds? Let's see, there's water, right? Two different elements, that's a compound. How about N2O4? Yep, that's a compound, two different elements. How about NaOH, which is sodium hydroxide? That's a compound. How about MnO2, manganese 4, I'll explain that to you later. Manganese, Roman numeral 4, oxide. That's a compound. HF, hydrogen fluoride. That's a compound. All of those are compounds. Okay, so now that we've identified elements, compounds, we're going to define a pure substance. A pure substance is anything that has the same composition no matter what you do to it. For instance, it could be an element or it could be a compound. But if you can separate, if you have a substance and you can separate the parts of it by physical means, in other words, you don't change the identity of the components, you just separate them. Like our sugar water, we separate the water from the sugar. Now we have two compounds. Those compounds are pure substances when they're separated. An element that has nothing else in it, like gold bullion. I like that one. Gold bullion, that's a pure substance. It only has gold elements in it, atoms in it. Okay, there are examples. Water, distilled water is pure. Carbon dioxide gas, you can get it in a cylinder, you can get it in little pieces, chunks, dry ice. That's carbon dioxide. That's a pure substance. Hydrogen gas, that's a pure substance. And gold, my favorite. Now, if you combine two or more pure substances, you get a mixture. Now, this is assuming that those substances do not react with one another. They do not undergo chemical reaction. If they do, then you've changed the identity of everybody, and now you've got a different description that has to be made. It could be a pure substance, or it could be a mixture that results. But in this case, we're just saying this is a physical phenomenon. When you put two or more pure substances together, you get a mixture. And the mixture can be separated into those pure substances by physical means. The other characteristic of mixtures is that they have variable composition, unlike compounds that have fixed composition of the elements. Mixtures have variable composition. For instance, you can make sugar water with just a little bit of sugar in it, or you can put a whole lot of sugar in it, like you're making hummingbird feeder juice. You put maybe half and half, a cup of water and a cup of sugar, and dissolve it and then put it in your feeder. Well, the composition is different between those two examples, right? That's characteristic of mixtures. It can have different compositions. Wine can have a different composition. Say you have pop wines or fruity wines that are maybe 5 or 6% alcohol by volume, or you can have vintage wines that are close to 12 to 15% alcohol by volume. Coffee can have a different composition. It's a mixture of water and caffeine and some other chemicals that are extracted from the coffee beans. And you can make it strong or you can drink it weak, right? It has different composition. Wood is a little more difficult to wrap our minds around, but different trees, different plants that use wood in their structure have different composition of wood. So we divide them in, say, softwoods and hardwoods, right? Pines are generally considered softwoods, and oak and maple are hardwoods. They have different composition to make them hard or soft. All right. So we can also characterize mixtures in terms of whether that composition, once we've established the composition, is it uniform throughout? In other words, if you subsample the substance here or here or here, it will have the same ratio of components everywhere. It's uniform throughout. That's called a homogeneous mixture. Homo means same. A solution is another way of saying a homogeneous mixture. We normally think of solutions as mixing a solid into a liquid, and then the whole becomes a liquid. That's one type of solution, where you put, say, sugar into water. A solid goes into water, it dissolves, and it's uniform throughout. That's a solution, a homogeneous mixture. There's no variability, no matter where you look. Here's an example of a homogeneous mixture where we put, that looks like sugar, it could be salt. I bet it's sugar because of the change in color. Once you get large amounts of sugar dissolved in water, the color tends to turn sort of a faint amber. And the solubility and how much of the substance that can go into the solution is different for different substances. Salt has its limit. You can put so much salt in water, and at a certain point, you can't put any more. It won't hold it. Sugar's the same way. But sugar, you can put enough sugar in water that at some point you've got more sugar in there than you have water. That's how it's very soluble. Other types of homogeneous mixtures. Air. Air is a homogeneous mixture of different gases. Nitrogen, 78% nitrogen, 21% oxygen, about 1% argon, and then minor components. That's a mixture. And it's interesting that gases of any kind, when you put two or more gases together, they always form a homogeneous mixture, a solution of gases. And it's reasonable because remember, gases, the molecules are very far apart and they don't interact. They're moving really fast too. So when you put two gases together, there's room for everybody. So gases always form homogeneous mixtures. But counterintuitive to that is homogeneous mixture of solids. Brass is an example. If you mix copper and nickel in the right proportions, it's primarily copper, about 75% copper and 25% nickel. And there are various compositions. But that mixture, once you put the solids together and melt them and mix them together and let them re-solidify, now you have a solid mixture, a homogeneous mixture of copper and nickel. Okay, so this must be salt. Table salt stirred into water. I would have guessed sugar, but it's a homogeneous mixture. On the other hand, heterogeneous mixtures, hetero means other. Heterogeneous mixtures are those in which the pure substances that you mix together never produce a uniform distribution or composition throughout. It's variable throughout. And there are a number of examples of that. Let's see. This must be sand and water. Yeah. If you put sand in water, then you get a heterogeneous mixture. If you put oil and vinegar, first of all, they don't like each other. But if you shake them up really hard, then you can distribute the oil throughout the vinegar temporarily. But it's not uniform. And eventually the oil will separate and rise to the top. So if you like to make your own salad dressing, you can take oil and vinegar and put them together. And I like to throw in some Mrs. Dash for a flavor and just shake them like as hard as you can in those little those Armor chipped beef containers, little glass containers with a blue cap on it. They're perfect size to make 1 or 2 servings of dressing. And you snap the cap on and shake it really hard and then pour it on your salad before it separates. That's a heterogeneous mixture, as is sand stirred in water. All right, which of the following is a homogeneous mixture? Okay. First of all, when you are confronted with a problem, first thing you need to do is say, what's the question? In this case, there's just one question, but some word problems have lots of information and then there's a question. So find out what the question is when you read the problem. Look for the question, because if you don't know what the question is, you'll never get the answer. Then you devise a way to answer the question. Sometimes it involves calculations. Sometimes it involves logic. And in this case, we're looking at this question, which of the following is a homogeneous mixture? So I approach this question backwards. Which of these are actually mixtures? Right? And you can, by process of elimination, you can weed out the ones that aren't mixtures. Then you can go to whether they're homogeneous or heterogeneous. So the first one, pure water. It's not a mixture. You can throw it out. Gasoline, that's a mixture. Jelly beans, mixture. Soil's a mixture. Copper metal, pure substance. Throw it out. So now we have these three in the middle, gasoline, jelly beans, and soil. We have to decide which one is homogeneous. Well, gasoline is a solution of octane, which is a hydrocarbon, and other additives. Nowadays, the first additive is ethanol. They add alcohol to our gas. And then companies will add proprietary components that they claim will clean your carburetor and keep your engine clean. So gasoline is a homogeneous mixture. How about jelly beans? Right? Look at any jar of jelly beans and you can see for yourself that it's not homogeneous. Right? You might have a whole bunch of greens over here with a red or the black maybe. And then on the other side, you may have more blacks and more reds and few greens. So you can tell by just looking at the jar that jelly beans is heterogeneous. And soil, take my word for it, soil is heterogeneous. My PhD is in soil science. And if you, particularly if you want to see heterogeneity of soil, just observe when you're driving through a road cut. And there are lots of those in West Virginia. And look at the top layer before you get to the rock, look at the soil. And the top layer has plants growing in it and it's kind of dark. And then below it, usually it'll get lighter color. That's indicative of a change in substance, a change in the mixture and what's in the mixture of the soil. Soils are heterogeneous. By the way, when you're looking at that change as it goes down in the soil, that's called the soil profile. Okay, so gasoline is the only homogeneous mixture in that group. So we can separate these mixtures by physical means. And these are examples of various ways to various properties, physical properties upon which we operate to separate the mixtures. So if you are separating a mixture based on boiling point, the technique that you're using is called distillation. You will take the mixture, heat it up, and the substances that are in the mixture will boil at different temperatures. So the more volatile ones will come off first, and then you can condense them and catch them. The next volatile ones, as you heat it up further, they will come off and you can condense. Now you have those separated. That's exactly what moonshiners do. When they have their big metal tanks and they put their mash and sugar and whatever, corn mash and sugar in there, water, and their starter culture, yeast, and cap it off, keep the oxygen out of it, and it works. The yeast work on the sugars in there, convert them to ethanol and some other things. So now you have a heterogeneous mixture in a homogeneous mixture, a solution with a mash in it. So you have a combination. And then you light up the burners underneath that metal tank and boil the liquid that's in there, and things start coming off, and you condense them and catch them on the other side. The first thing that comes off when the moonshiner is distilling the mash is methanol. That compound, methanol, comes off first. You don't want to sell that to your customers. If they drink that sufficient amounts, they'll go blind. It could kill them. So the first thing that comes off when you distill, you catch it, and with experience, you know when you can stop catching it, and now you've got the next component coming off, then you throw that away. That's poison. The next thing that comes off is ethanol. That's where your money is. You've distilled off the methanol, now the ethanol comes off. And it comes off also, it's the nature of ethanol that there's a co-distillation there, that ethanol and some water comes with it. But you're separating the components using distillation and a difference in boiling points. Okay, another one, states of matter, right? Solid, liquid, or gas. We can use filtration to separate them. So if you have a solid suspended as a mixture, suspended in a liquid, then you can filter it through an appropriate membrane with the correct pore sizes, and you can catch the solid. You can actually separate liquids and gases through filters. I won't go into the details, but we used to use those type of filters on some systems in the lab where I was previously employed. They would keep water condensation out of the gas before it goes into your instrument. Water in the gas would be bad for the functioning of your instrument, so we used a filter that would filter out the liquid. If you have a differential adherence of the substances in your mixture to a surface, then you can use a process called chromatography. Originally, the first chromatography was done on paper. And it was an extract, an alcohol extract of leaf tissue. So we would have this container, and we would have some liquid down here, probably ethanol. Didn't have to be, but it could have been. It could have been water. And we would take a piece of paper, and on this line, we would spot extracts of our leaf tissue. Then we would take the paper and we would set it over here in this container, and the spots would be here. And then we put a lid on it. And the paper would imbibe some of the liquid, and it can start moving up the paper, primarily through capillary action. But as it moved, it would dissolve those spots. And the components inside the spot, this mixture of things that we've extracted, would be differentially adhered to the paper. They would be attached to the paper for a time, and then they would go back into solution and move some more, and adhere to the paper and go back and move. Well, the ones that were the strongest attracted to the paper would move the slowest. So they would be down here. They would have a line here. And then the ones that weren't attracted strongly to the paper would move faster, and they would be up here. Right? So you could separate your mixture by this process called chromatography. Chroma means color, and graph means to write. So it's color writing. But it's a physical process that separates things. If you use just pure volatility, right, you can just evaporate, right? If your mixture is salt and water, all you have to do is evaporate the water and you get your salt back. That's kind of a variation of distillation. Of course, you wouldn't distill the salt. You can't get the temperature hot enough to do salt. So we consider it a non-volatile compound. All right. There are many other ways to do this. They're all based upon physical properties, and we can separate mixtures. This example is the one on the left is distillation. Right, so we can separate volatile compounds and catch them differentially as they come off. And the way we know in the laboratory, I've done this, in the laboratory, you know when the next component is coming. The first component comes off, you read the temperature right here with this thermometer. And it'll stay at that temperature until you've gotten all of your component off and it's condensed and collected in the vessel. And then you see the temperature start to move, then you remove that vessel and put a new vessel in. You're catching the next component at the next higher temperature. And you can keep doing that sequentially and catch each component with its different boiling point that you measure here. This is just simple evaporation. We just heat it up and there's a Bunsen burner. You just heat it up and remove the water as vapor. And if you want to, you can condense it, which is what we've done here. Condense the water vapor and catch it over here. And now you have salt and water separated. Okay. The important fact here is that no chemical change has occurred. The substances in the mixture have their individual identities, and those identities are retained in the process. This is an example of filtration. You have a funnel, and we have a filter paper in the funnel, and all we have to do is pour this mixture through the filter paper and catch the solid, and the liquid goes through. Now, it doesn't separate everything. Suppose your liquid had, it was a salt solution, plus you mixed a little sand into it. Well, there you have a heterogeneous mixture of salt, water, and sand, but a homogeneous mixture of salt and water, right? A combination. All right. So this is just a flow chart to give you some idea of how we separate and characterize things. We have matter. We can make mixtures out of them. We can make a homogeneous mixture, a heterogeneous mixture. You can use physical means to separate the components, right, into pure substances. Or there's a case where the matter itself may already be a pure substance. Right? That's possible. Then if you have pure substances, the only way that you can separate the pure substance into components is by chemical means. And the pure substance could either be an element or it could be a compound. Okay? And the element, of course, you can't reduce it any further. But the compound, you might be able through chemical means to change it into elements, separate the elements. Okay. So we're finished way early. Got any questions about what you've seen so far? What we're going to do is we meet on Tuesdays and Thursdays. Well, I do. I Zoom and record the meeting, and most of my students are attending through only on the web. So they view the recordings later, and they submit their homework assignments and exams online. The homework, you have to buy Cengage Unlimited. If you've already got it from another course, then you don't have to buy it again. You just have to register through Brightspace. You have to go into Brightspace and register for the homework through that course. That way, your homework and Brightspace are linked. And when you complete an assignment in Brightspace, in Cengage, excuse me, then the results are sent to the Brightspace gradebook, and I can see them. So that's homework. Exams. If you're going to take an exam online, then you need a Respondus Monitor and Lockdown Browser. So if you've taken other courses that use that, there's no difference. It's the same type of process. In Brightspace, you'll go into each of the modules and find the exam that says Exam 1 with Respondus Monitor and Lockdown Browser. And you click on that. And then if you don't have the browser and Respondus installed on your computer beforehand, then there's a place at the bottom right before you click on Start the Test that says Install. And you can install Brightspace at the Respondus Monitor and Lockdown Browser from that place. Then you can go. But one thing you do want to do is, if you haven't already done it for another course, is take the practice exam. The practice exam is in there so that you can test your equipment and be sure everything's working before you try to take a bona fide exam with this monitoring system. Then if you have trouble, you can contact me and we'll work it out. Either I'll fix it or we may have to go to IT depending on how difficult the problem. Oh, by the way, homework. If you're having trouble getting your homework registered, or you have any technical difficulties, up through February 15th or 17th, Cengage is offering IT support through what they call office hours. And there's a link in Brightspace, you've probably seen it. And you just click on the link and it will connect you with, during the hours that they list, connect you with someone that'll help you work out the problems. Let's see. Next time we meet, Thursday, we will do a review and use the review document that's in that module 1 for exam 1. Hopefully by that time you will have tried to work some of those problems, answer questions, and check your answers with the key that's also in that module. And then if you want to, you can attend class and ask me questions about it. And we'll work out your problems first before I start talking. And I've got the review document. I've picked out a few questions that are non-redundant and cover the main topics in those 3 chapters. And that way you can focus your energies on stuff that'll do the most benefit for exams. And then the following Tuesday, a week from today, the exam 1 will be due. If you take it online, it'll be due by midnight. If you come in person, I'll give you a paper copy and you take the exam during the class period, and I'll grade it before you leave class, so you'll know what your grade is. If you take it online using Respondus Monitor and Lockdown Browser, the system will grade it for you and will tell you what the grade is when you finish it. I don't think of anything else that could potentially be the problem or you need to know.
Mr. Blah.
Yes.
How do you count the attendance if we go back later and watch the Zoom? If we're not like physically present on Tuesday or Thursday?
Right. You know, the dean asked me that the other day. When I have only Zoom or face-to-face classes, you have to show up in class or be on Zoom for me to count you. But when there's a web component added to it, like this course, this is what's called HiFlex. You can attend any way you want to. I have to judge your attendance. If I don't see you in face-to-face or Zoom, then I count your attendance by completed assignments.
Okay.
So if you complete your homework on time and your exams on time, then I count you as present. And let's see, what do they use? My mind's gone blank. There's a there's an app that we use to record attendance.
Okay.
And I'll report non-attending for this class. Just if you go, say you go a week without finishing an assignment, then I'll report an absence.
Okay, because the reason for my question is I can log on from work, but I probably, as far as like having an open discussion, I don't know that, if you like ask questions and want answers back.
Okay. Well, I do extemporaneously during class, but I rarely get an answer.
Okay.
So if you're in a situation where responding would be disturbing to the people around you, then you don't have to.
Okay.
And I know some instructors have these built-in quizzes that they do through Zoom. I haven't been ambitious enough to create any of those.
Okay. Thank
So,
you.
focus on the review document. That'll take you in the proper directions for understanding the material. And I've set it up. These review documents look exactly like paper exams. And some of my students actually do that. They take them as if they're an exam, then go use the key and grade them, and they find out where they're weak and work on those things. And then they come to class it's only face-to-face. They come to class and we discuss those items that they're having difficulty with first, before I go ahead and do my talk.
Thank you very much.
Okay, so I guess we're done for today. I mean, it was kind of a short lesson. Doesn't always happen that way, but today it did.